All right, so in our last video for this chapter, we're going to talk about titrations and how you do calculations for those. So, basic idea here, right? No pun intended. Um, Sodium hydroxide and hydrochloric react together to make water and a salt. But once they do that, I have a neutral solution. So, I can use this reaction, right? Titrating one thing with the other to find out the concentration of one of those two solutions, whether it's the sodium hydroxide or the hydrochloric acid. So I have to have something that I know, right? In this case, and typically it would be that sodium hydroxide, right? I know the concentration of the sodium hydroxide. What I don't know is the concentration of the hydrochloric acid. So I'm going to use a standard solution, a sodium hydroxide solution, to find out what concentration of acid I have. So all I'm going to do is add that base to my acid until my solution is neutral, right? And I can find out when that solution is neutral when I see certain things, right? The first thing I could do is I could have a pH meter that's just reading the pH constantly as I add drop by drop of that sodium hydroxide. And eventually that pH is going to go from very low, being as it started as an acid, to 7 to neutral, and then it would actually go into that higher end of the spectrum as well. But you could figure out when it hit 7, and that would be your equivalence point, right? I'm looking for a point where the amount of sodium hydroxide is equal to the amount of hydrochloric acid because they've reacted together and all you have is water and salt. So I want to add my base until the pH is 7, but that's not always going to be a simple, easy task, right? Instead of watching the pH, which will actually change drastically when it gets close to that 7, that neutral, instead, we usually use an indicator, right? So a pH indicator that'll change color when I reach my equivalence point is the easiest way to do this, right? So I'm going to show you guys how this would work in class. But I just add base until the color changes for my solution, right? The color will change and then it'll go back to clear. The color will change again and then it'll go back to clear. But the longer that color persists, the closer I am to my endpoint. And like I said, it's going to be easier to show you than describe how this works. But at the end of the day, it's going to be something where I get certain information out of the lab. So I'll know how many milliliters of my sodium hydroxide it took to titrate my acid. So I have to do a calculation with that. I'm going to use milliliters of my known. Again, in this case, my known thing is the sodium hydroxide. So I'm using blue for bases, right? I'm going to know how many milliliters it took to titrate my acid. And then I'm going to use the molarity of that sodium hydroxide, so I should know the concentration for that sodium hydroxide. Now, in the calculation, I would rewrite that. Again, molarity is moles per liter. So if I just split that up here, moles per liter, right, of my unknown, or excuse me, my known. So again, I know this concentration. I was given this concentration. That's what I'm going to put here. The liter just goes down here by default because it's a complex unit. And then you got to think of it right now as if this milliliter and this liter canceled out, right? I know that they don't, but I'm not actually going to do anything about it because it's going to take care of itself in a second. The next thing I need to do is, now that I have moles of some substance, my sodium hydroxide specifically right now, because that was my known concentration, I need to do a ratio, right? Because for every 1 mole of that sodium hydroxide, my known concentration, so again, I'm highlighting it blue instead of labeling it as sodium hydroxide, but you can figure that out. For every 1 mole of sodium hydroxide, 1 mole of my acid will react because these things are in a 1-to-1 ratio. We'll talk about what happens when it's not a 1-to-1 ratio, right, in a problem here in a second. But otherwise, now that I've done that mole ratio, now I'm talking about my acid, and there's a certain amount of that acid that was in the original sample that I was titrating. And that's the last thing that I'm going to know, right? I'm going to have a certain number of milliliters of that acid that I started with. Not sure why I wrote moles there. But this is where, what I was talking about before, this is where that milliliter takes care of itself, right? I started out with a milliliter over here, and it's going to cancel this milliliter all the way over here. My moles of base cancel. So now I have moles of acid, and this liter that was here already is part of my end unit. This is supposed to tell me the molarity of my acid when it's all said and done. So again, I didn't know the concentration of my acid, but using the data from the lab, I'm going to be able to calculate it. So at the end of the day, what happens here can be simplified into an equation that looks like this, right? Because I have a volume of my base, and I multiplied it by the molarity. So I might put VB, MB, or in the other order, it could be MB, VB, right? Doesn't really matter which way because I'm multiplying here, right? Those will be equal to the molarity of my acid times the volume of my acid, right? So I started with V first on the other one, so I'll do that here too, right? So it might look like this. I actually typically would write it this way instead, but I literally did volume times molarity. But this is the exact same thing as what I just wrote. So typically, you see the equation look like this. Sorry, I screwed up over here actually. So one way or the other, don't care which equation it is because it doesn't really matter which variable you put first. But you multiply your molarity and your volume on both sides, but one side is for your base, one side's for your acid. This equation will typically give me the same answer as this work above, right? But I can only use this equation if I have a 1-to-1 ratio. So that's the trick. Sometimes you're going to have to do it the long way. If this is not a 1-to-1 ratio right here, if it doesn't take one acid to react with one of your moles of base, then this won't work, right? So I do have a shortcut that I can use, this equation, but I can only use it when it's a 1-to-1 ratio. So let me show you some examples so you know what I'm talking about, right? So I have a 15 milliliter sample of nitric acid. I don't know the concentration of it. And it was titrated with a 0.109 molar sodium hydroxide solution. And it takes 18.6 milliliters of my base to neutralize my acid. So the question is asking, what is the concentration of that nitric acid? All I have to know is what's my acid, what's my base, right? I know the volume of my acid. I don't know the concentration, right? I know the molarity of my base, and I know the volume. So if I take my molarity that I know times the volume for that substance, and I multiply them, that should be equal to X, or the 15.0, because again, it doesn't matter what order you do it in, times the concentration that's unknown, right? That's my X. I can just use an M for that. Doesn't really matter, right? Since it's supposed to be a molarity, that's why I'm using an M. But just solve for what's missing. So divide the 15 across, and you can get your answer. When I punch that in my calculator, I get an answer of 0.13516. I do need to round this to 3 sig figs. So apparently my concentration is 0.135 molar, right? That's the concentration of my acid. Maybe I'll put that at the end of it, HNO3, right? So that's what I accomplished, right? I found out the concentration of that acid through titration. So that was a simple example, right? This one's going to be a little bit more complicated. The reason it worked the way that it did here, though, I forgot to do that step, so I need to show you, is that when I react one of these acid molecules with my base, again, there's a reason you had to learn how to do this in the last video. I'm going to make a water, and I'm going to make salt, right? It happens to be sodium nitrate in this case. But when I balance this, it's all 1 to 1 to 1 to 1. This is a 1 to 1 ratio. I'm allowed to use this equation if it's a 1 to 1 ratio, and only if it's a 1 to 1 ratio. On this next example, I'm going to have this acid that is called phosphoric acid. You don't have to know what those acids are called, but just letting you know. So if you hear it once, maybe you'll hear it again in the future and it'll catch on. So I'm going to have this phosphoric acid and sodium hydroxide that react. Again, I taught you earlier that one hydrogen and one hydroxide should make a water, but I also have to make sure that this is balanced because I have 3 hydrogens. So I should need 3 hydroxides to make 3 waters when it's all said and done. So I know that I'm going to need a 3 here, which gives me a little hint. Tells me that when I balance my salt, I'm probably going to need a subscript 3 right there because I need 3 sodiums to go with 1 phosphate because phosphate has a -3 charge, sodium has a +1 charge. So again, if you're thinking when you're doing this, it's not that hard to figure it out. You don't even have to look up what the charge is because you should know from the problem. But otherwise, this ratio over here is not a 1 to 1, it's a 1 to 3. So I have to do this one the long way, right? So I'll show you how this one would work, right? So again, I know my base stuff, right? I know it took 50 milliliters of base to neutralize my acid, and I know that my concentration of my base is 0.100 molar, right? So if I start with what I know for the base, my 50 milliliters, and I know the concentration, so I'm going to write that a little bit different because I like to split it up. I got moles here per liter. All of that would be labeled, right? Sodium hydroxide, but I'm going to go ahead and just highlight it instead because it's easier for me on this. And then I do a ratio here, but I need the ratio of my sodium hydroxide on the bottom, and that was a 3 with my sodium hydroxide, right? Sorry, I actually don't want to write sodium hydroxide. I want to write moles. I'll infer that it's sodium hydroxide by highlighting it. But otherwise, I had 1 mole of acid that reacted for every 3 moles of my base. So now I have a label change. Now I'm talking about the acid, not the base. So sodium hydroxide, phosphoric acid. So then finally, the last step, I told you to put the milliliters for your acid, which was 50 in this case, on the bottom over here. Highlight that, right? Or write H3PO4 behind it. But this should have gotten me from molarity of one thing to molarity of the other because the milliliters cancel. Like I said, it's a long distance cancel, but it works. I still got moles per liter, but it's red now, right? A red mole, which means that I have a concentration of my acid. And in this case, if I plug it into my calculator, I'm pretty sure I'm going to get a 0.033333 repeating, right? I should have 3 sig figs because all the numbers did. So I'll round that appropriately. And I know that I have a 0.0333 molar concentration of my acid, that H3PO4. But again, can't do this with a shortcut because you have to include your ratio. If it was a 1 to 1 ratio, I would have done it the same way I did it on the last slide. So always check, how does that acid and base react? How do they react? Because if it's not a 1 to 1 ratio, it makes your life a little bit more complicated.